In this lesson, we'll be expanding our examination of acids and bases by looking at weak acids and weak bases. Up to now, we've only discussed strong acids and bases, which ionize completely in water, meaning every molecule breaks apart into its ions. Weak acids and bases behave very differently. On this slide, you can see that weak acids and bases are associated with an equilibrium. That's because weak acids and bases only partially ionize. Only some molecules break apart, while many stay together. We'll also discuss a more general model for acids and bases, the Brønsted-Lowry model. By the end of the lesson, you'll be able to apply the concepts of chemical equilibria that we've already discussed to solving for the pH of a weak acid or weak base. So the Brønsted-Lowry model is a little bit more general than the Arrhenius model was. Rather than saying that it has an acidic hydrogen in the front, the acid in the Brønsted-Lowry model increases the hydrogen ion concentration in a solution by donating a hydrogen ion. And then bases are going to increase the hydroxide ion concentration by accepting that hydrogen ion from the acid. So here we have a very generic reaction equation for a weak acid. The way you look at it is you have to examine both sides of the equation. So we see on the reactant side we have HA, and over on the product side we have just A minus. So that means that HA lost its hydrogen ion, it donated it. So if HA is the acid, the hydrogen donor, that means water has to be the hydrogen acceptor, which makes it the base. Now, we're not used to thinking about water being an acid or a base, but that's why the Brønsted-Lowry model is a little bit more general. It encompasses some of the exceptions to the Arrhenius model. Now, if we want to look at the other side and kind of do the same thing, but look at the reverse reaction, here we see we have H3O plus, that's called the hydronium ion, losing a hydrogen ion and going back to being water. So therefore, H3O plus is going to be our hydrogen donor on the product side, and the A minus is going to be the hydrogen acceptor. Now, it's going to be really confusing if we have acids and bases on both sides of the reaction equation. You want to make it clear whether you're talking about what you initially mixed together or what was formed as a result of this dissociation. So the hydrogen donor on the product side is going to be called, the hydrogen acceptor on the product side is going to be called the conjugate base. It's kind of like when you have conjoined twins, they're joined together by something. The HA and the A minus are joined together, they're part of a pair. And then that makes the hydronium ion the conjugate acid. Notice that acids make conjugate bases and bases make conjugate acids. So here's another example. So again, we compare the reactants and the products, and we see when we have NH3 on the reactant side, it becomes NH4 plus on the product side. So that means it accepted a hydrogen ion. So NH3 is the base, which makes water the acid. And then NH4 is going to be the conjugate acid, and the hydroxide is going to be the conjugate base. Typically when you're doing this, you should end up with hydroxide being the base, because that's what gives gives substances their basic character. Substances that can act as either an acid or a base, like water, are called amphoteric. Ter is a word stem that means solvent, and then ampho is kind of like ambi in that it means it can go either way. So the self-ionization of water is a really important part of any discussion about weak acids and bases. So self-ionization of water just means that water will spontaneously break apart into hydrogen ions and hydroxide ions. Now, in truth, you don't actually have free hydrogen ions in solution. That's essentially just a proton. It's not going to be unassociated with something else. A better way to represent this is that you have two water molecules. One is giving up a hydrogen ion and the other one is accepting a hydrogen ion. So we're going to be forming the conjugate acid, which is the hydronium ion, and the conjugate base, which is the hydroxide. You can do it either way. I prefer the first one, even though it's less realistic because it's a little bit easier to write. So we're talking about an equilibrium. And since this one is very important, it gets its own little subscript. So Kw refers to this equilibrium between the undissociated ion, water and its ions. Remember, we leave out liquids because they have an activity of 1. So we end up with that Kw, which is the hydrogen ion concentration times the hydroxide ion concentration, is equal to 1 times 10 to the minus 14. And this is true at room temperature, 25 degrees C. In neutral water, these two substances, these two concentrations are going to be the same because for every one hydrogen ion you got, you're going to have the same number of hydroxide ions. So that means you just take the square root of 1 times 10 to the minus 14, and we get 1 times 10 to the minus 7. Now that we know what our hydrogen ion concentration is, we can find the pH of a neutral solution, and we get, unsurprisingly, that the pH of a neutral solution is 7. So just in case you were ever wondering where that number came from. So like I said, previously we've been talking about strong acids. Now I have a list of the strong acids. So we have, and strong acids are ones that ionize completely in solution, and there is no equilibrium. So we have, there are, these first 5 are the ones that are truly strong acids. They ionize completely. With sulfuric acid, only the first hydrogen ion that comes off is strong. The other one is moderately strong, but it usually gets thrown in with this list just because it's another mineral acid. So you can either memorize this list, or you can notice that we got hydrochloric, hydrophobic, hydroiodic. So hydrofluoric is not a strong acid. And then, but they all go down the halogen column. And then we have perchloric and nitric and sulfuric. So these are like the maximum oxidation level for the polyatomic ions. And because they ionize completely, we don't have to worry about equilibria. So we can just take the concentration of the acid, assume that all of it has ionized, and do negative log of whatever the acid concentration was. And so for our example, the pH would be 3. And we could have guessed that just by looking at the power on the 10. So weak acids only partially ionize in solution. So that means that there's going to be an equilibrium. So we have our generic form of a weak acid, HA. So it's going to ionize into the hydrogen ion and the conjugate base, A-. So we're going to give it a special designation of Ka. The A just reminds us that we're talking about a weak acid. That's another way that you can tell that whether you have a weak acid or a strong acid is if the problem says anything about Ka, it means you have a weak acid. So we go ahead. We say, all right, what is the pH of a weak acid if at equilibrium the concentration of HA is 1 times 10 to the minus 4 molar, and it has a Ka of 1 times 10 to the minus 5. So this is where you have to use a little bit of your stoichiometry. You have to remember that for every one of those, every hydrogen ion, you're going to have the same number of conjugate base. So therefore, these two concentrations are going to be equal. So I solved it a little bit ahead of time. So the hydrogen ion concentration squared is equal to Ka times the equilibrium concentration of the non-dissociated weak acid. Put the numbers in, and then take the square root of both sides, and you get that the hydrogen ion concentration is 3.16 times 10 to the minus 5. So here's finally one where we can estimate it, and it's not going to be just the power. So we know that the pH is going to be close to 5. We take negative log, and we get 4.5. So like strong acids, strong bases also ionize completely in solution. And examples for strong bases are going to be group 1 and group 2 hydroxides. Sodium hydroxide is like the most common example, I think, that I can think of for a strong base. This is what is the active ingredient in Drano, incidentally. So weak bases, they're also going to have an equilibrium. So we write out our equilibrium expression. Going to be products over reactants. And we're going to put a little subscript on the equilibrium constant of a B to indicate or to remind us that it is a weak base. All right, let's do some calculations. So what is the pH of a 0.15 molar solution of a weak acid if Ka equals this? Oh, and I should say for anybody that's listening that is at an advanced level, we're going to be assuming that the initial amount of the weak acid or the weak base is not changed at all as a result of the dissociation. So we don't have to set up ice tables. So we write out the reaction equation. Write out the Ka expression. Substitute in the values. Not advancing. There we go. So we have for every, we're trying to get at pH, so which means that we want the hydrogen ion concentration, and the hydrogen ion concentration and the conjugate base concentration are going to be the same. So then we're going to solve for H plus. And then now we just take the negative log of that, so it's going to be close to 3. And we get that we have a pH of 2.6. And just in comparison, if you were to figure out, just assume that this is a strong acid, you would end up with a pH of 0.82. So you can see that equilibrium being present has a big impact on the final pH. So our next example, what is the Ka of a weak acid if a 0.15 molar solution has a pH of 4.7? So the steps are very similar. So write out the reaction equation. It's the same thing because we're talking about a generic weak acid. Write out the Ka expression. Now this is where it's a little bit different than the previous problem. We're going to undo the little p function to find what the H plus is. We saw this once before when we were doing the general pH calculations. So H plus is going to be equal to 10 raised to the negative pH. So we go 10 to the negative 4.7, hit equals, so it converts it into standard notation, and we get that our H plus concentration is 2 times 10 to the minus 5 molar. Substitute in the values. So we know that Ka is equal to x squared divided by 0.15. So we do 2 times 10 to the minus 5 squared divided by 0.15, and we get a Ka of 2.65 times 10 to the minus 9. So this is a really weak acid. Just to give you an idea, vinegar has or acetic acid, I should say, has a Ka value of 1.8 times 10 to the minus 5. So this is roughly 2 times weaker than acetic acid is. So another example, we have a weak base in this case. We can tell that it's a weak base because we have that Kb right there. And I'll call that out as well. So again, write out the reaction equation. So I've never really been able to come up with a good generic base a way of expressing the base. On the wrap-up slide, I just use capital B. I guess you could use that. It's just, I don't know. It never quite sat right with me. So I have the full equation for aniline formula. So now we write out the Kb expression. Remember, water is a liquid in this case, so it's going to be left out. Substitute in the values. So we have our Kb is equal to x squared divided by 0.3. So we're going to multiply both sides by 0.3 and then take the square root. So we end up with a hydroxide concentration, because it's a base, of 1.14 times 10 to the minus 5 molar. So we find the pOH, which is equal to something around 5. So 4.94, subtract from 14, and we get that the pH of a base, of this weak base, is 9.06. Again, when you're doing these pH calculations, you want to do reality checks to make sure that the pH makes sense. So if you're finding the pH of an acid, it should be below 7, and the pH of a base, it should be above 7. All right, so that's it for talking at you about weak acids and bases. So just to wrap it up, we have the Brønsted-Lowry model. It's a more general model than the Arrhenius model. It says that acids are proton donors or hydrogen ion donors, and they're the ones that form the conjugate bases. And bases are proton acceptors, and they form conjugate acids. Weak acids and bases only partially ionize in aqueous solution as compared to strong acids, which completely ionize. And there's going to be an equilibrium between the undissociated species and the ions they produce. So for weak acids, we have this generic equation, and then for weak bases, here's where I tried to make a generic. So we have the base plus water gives you the base with where it's accepted a hydrogen ion and its conjugate base of water. So we can use the Ka or Kb values to get a sense of the relative strengths. So the smaller the values are, the less ionization there is, and the weaker the acid or the base is going to be. And then because we have an equilibrium, we have to use the equilibrium expression when we calculate pH calculations for weak acids or bases. So that's it for our weak acids and bases. Look forward to seeing you in the next video.